I'm very happy for the opportunity to give this presentation. My name is Anca-Cristina, and my presentation today focuses on experimental work performed during my doctoral studies with Professor Frank Vecchio at the University of Toronto. It is titled Alkali-Silica Reaction-Affected Reinforced Concrete Elements Subjected to Pure Shear. These images show two bridges with visually alarming cracks caused by alkali-silica reaction, ASR. Both bridges had to be demolished, their replacement costing hundreds of millions of dollars. The scope of my doctoral research program was to better understand the behavior and to enhance the numerical modeling of such structures. Aging, deteriorating infrastructure is a salient issue in North America, and the environmental and economic challenges that we face today dictate a more prudent maintenance of the already built infrastructure. So here is the outline of my presentation. First, I will introduce the alkali-silica reaction, followed by the presentation of the experimental program undertaken, specimen description, discussion of the experimental results, and I will end with conclusions. Deleterious ASR develops when the concrete mix contains reactive aggregates that are susceptible to alkali attack. The reactions between alkali hydroxides and the reactive aggregates produce a gel which, if water is available, it absorbs it, the pressure buildup causing expansion and cracking. There are several factors that influence the rate and the severity of the reaction. And now let's take a quick look at the typical crack pattern that develop in ASR-affected structures. So for a structure that is relatively unrestrained and free to expand, a map cracking type of pattern is most likely to develop, like we see in the first figure. For a structure that is not free to expand due to either internal or external restraints, like the second figure, the cracks, the ASR-induced cracks developed will most likely be parallel. So in the second figure, we see a biaxially reinforced panel suffering from ASR that I tested, and it contains significantly higher reinforcement ratio in the X direction compared to the Y direction. The crack pattern parallel to the X direction indicates that the X reinforcement is restraining the expansion to a higher degree than the Y direction can. ASR deteriorated infrastructure poses several issues. One of them is increased seismic demand compared to sound structures. During a seismic event, because of the pre-stressing effect ASR has on the reinforcement, affected structures are expected to exhibit higher stiffness compared to non-reactive concrete structures, thus resulting in an increased demand. Several bridges around the world have been demolished around this consideration, including the 6th Street Viaduct in Los Angeles that I'm showing in the third picture. So let's continue briefly discussing the ASR-related structural implications. Two distinct mechanisms need to be considered: the ASR-induced pre-stress that I just mentioned, and the deterioration in concrete mechanical properties. As the reaction develops within a reinforced concrete element, the reinforcement acts as an internal restraint, developing tensile stresses and thus inducing compressive stresses in the concrete. At the same time, due to the cracking-induced damage, the concrete mechanical properties undergo a degradation that may significantly vary with the direction of the long-term principal stress. A survey of the literature found results showing both increases and decreases in the capacity of ASR-affected shear-critical specimens when compared to similar non-reactive specimens. The plot summarizes the mean ratio of the load capacity of reactive specimens to that of non-reactive control ones. These mean ratios range between 0.77 and 1.9. The contradicting experimental results in the literature served in part as motivation for the structural level experimental program that I'm presenting today. So in order to improve our understanding on the ASR effects on the response of reinforced concrete elements, we developed an experimental investigation involving panel specimens that were loaded in pure membrane shear. 10 panels were constructed and tested to failure, and shown in this figure is the test setup. The specimens were tested in the structural testing facility at the University of Toronto using the panel element tester. The panels, containing varying amounts of in-plane and out-of-plane reinforcement, were cast with either non-reactive aggregate, so these were the control ones, reactive fine aggregate, Jobe-Newman sand from Texas, or reactive coarse aggregates, Spratt from Ontario. The panel specimens were tested under either monotonic or cyclic loading protocol. So the loading on the concrete panel was applied around its perimeter through 20 shear keys. Each shear key was connected to 2 links. To produce pure shear, one link applied a tension force and the other link applied an equal compression force. The strain state was obtained from measurements taken by LVDTs. During the test on each face of the panel, 6 LVDTs measured the displacements along 4 directions as shown in this figure. The specimens were nominally identical, 890 millimeters square by 70 millimeters thick. For all panels along the X direction, a reinforcement ratio of 3.31 was provided. In the Y direction, the reinforcement ratio varied from 1.66 to 0.84 to 0.42 to 0.2%. These figures show a test specimen containing out-of-plane reinforcement before and after the cast. Each cast produced 2 panels, 3 plain concrete prisms to monitor the ASR expansion on plain concrete, and 9 standard 4-inch diameter cylinders. The specimens were moist cured upon casting, after which they were stored at ambient temperature until the accelerated conditioning process started. During the accelerated conditioning period, the specimens were maintained at a temperature of approximately 50 degrees Celsius and 97% relative humidity. The temperature and relative humidity were chosen having in mind 2 objectives: to increase the inherently slow rate of the ASR expansion and to minimize the effects accelerated conditioning may have upon the response of concrete. Expansion measurements monitored the longitudinal strains of the plane prisms that I just mentioned, stored in the same environmental conditions as the panels. The results are shown here for all 5 casts, and we can see that I chose the testing of the panels once this curve has flattened, so once the reaction has exhausted. In addition, strain measurements on the surface of the panels were also taken along X and Y direction using Zurich targets, as shown here at different intervals. So let's examine the measurements taken for the panels belonging to cast number 2, Jobe-Newman, and here's for reference the expansion measurements on prisms. So first, the lightly reinforced panel. Along the X direction, the reinforcement ratio of 3.31% is restraining the expansion significantly compared to the measurements taken on the prism. Along the Y direction now, which has 0.42% reinforcement ratio, the panel developed strains almost identical to the strains measured on the corresponding prism. The heavily reinforced panel developed strains along the X direction that were similar to the lightly reinforced panel, and along the Y direction, which now contains 0.84% reinforcement ratio, the measured strains are smaller compared to the ones on the lightly reinforced panel, yet still higher than in the X direction. So there's somewhere in between, but we can definitely see this anisotropic expansion that occurs due to different reinforcement ratios. Okay, next we're going to look at some brief information on the material characterization tests that accompany the test panel. So first, the reinforcement coupon test. As you can see, all 3 types of reinforcement were cold form, exhibiting no clearly defined yielding plateau. So a Ramberg-Osgood function was adopted to define the steel behavior for the analytical study. Concrete compressive tests were performed on cylinders at test day. The plot shows representative stress strain responses for cylinders tested in compression for 3 different casts. Note that at 80 days, all these mixes had a cylinder compressive strength of around 48 MPa. So it is evident that the compressive stress evolved differently for each cast, and the disparities for the reactive casts 3 and 2 are attributed to the ASR-induced damage. Okay, next we are going to look at the experimental measured responses. So here we see the shear strain versus the shear stress for 6 of the panels. Panel number 2 suffered an edge failure at the same time that the Y direction reinforcement started to yield, but the rest of the panels were carried through successfully. The failure was initiated by yielding of the y-direction reinforcement, which led to aggregate interlock failure and subsequently sliding along the cracks interfaces for the lightly reinforced panels, the first row. Crushing of the concrete in compression initiated the failure for the heavily reinforced panels, so the second row, which was a more explosive mechanism. The responses of the panels containing out-of-plane reinforcement are shown on the left-hand side. These responses and the failure mechanisms follow the same trends as the panels that had no out-of-plane reinforcement. On the right-hand side, we see the response of the panel containing the least amount of reinforcement, panel 9, which had along the y direction 0.2% reinforcement, comparing to the rest of the panels. In this case, the capacity reserve after the initiation of the first crack is highly reduced. And lastly, the panel that was tested under cyclic shear, with each cycle reaching a peak shear stress of 10.8 megapascals. Yielding of the y-direction reinforcement occurred only in the third cycle, and failure occurred during the 15th cycle due to concrete crushing. So next, let's examine the response of the lightly reinforced panels that contain the same amount of in-plane reinforcement. Panels number 3 and 5, shown here with yellow and green, contain the same amount of in-plane, had virtually identical responses despite differences in concrete compressive strength, notable differences in ASR expansion level, and moreover, panel number 5 presented no visual ASR-induced cracks that would indicate the occurrence of ASR. Compared to the control specimen, number 1, both panels had marginally higher ultimate shear stresses. The difference in shear strain at failure, however, was more pronounced as the reactive panels only reached on average 68% of the ultimate shear strain of the control panel. Another significant difference is the cracking strength. Due to the biaxial compression state of the reactive concrete, the load-induced cracks in the reactive specimens developed at shear stresses levels that were nearly double compared to the controlled specimen. As such, the margin between cracking at failure was reduced in terms of strength and deformation for the reactive specimens. Now, panel number 7. This panel had a slightly better performance compared to reactive panel number 3. Both panels were cast with the same type of reactive aggregate and contained the same amount of in-plane reinforcement. This slightly enhanced performance is attributed to the out-of-plane confinement stresses experienced by the concrete in panel number 7. Panels 3, 4, and 9, they were cast with the same amount of x-direction reinforcement, same type of reactive aggregate, but with different amounts of y-direction reinforcement. The panels developed ASR-induced cracks that were 80 millimeters apart, oriented parallel to the x-axis, which is shown in the first row of figures. Looking at the shear stress strain responses, the pre-cracking stiffnesses of the panels were virtually identical, and moreover, the cracking strengths were also similar. Post-cracking stiffnesses, however, diverged significantly, reflective of the reinforcement ratios in the y direction. The higher the reinforcement ratio, the stiffer the post-cracking response. In terms of ultimate shear stress, the panels reach 4.8 MPa, 7 MPa, and 9.8 MPa. As such, the cracking loads represented 81%, 62%, and 44% of the ultimate load. So the reserve capacity after cracking is reduced significantly with the reduction in reinforcement ratio provided. For all panels, the concrete principal tensile stresses at cracking were calculated and compared with the ACI 318 calculated tensile strength that's shown in the table, with the exception of the panels that contain out-of-plane reinforcement, which is 7 and 8, and the concrete principal tensile stress at cracking, so here labeled with FC1, were significantly lower for the reactive panels compared to the non-reactive ones and to the ACI 318 calculated tensile strength. The significantly reduced cracking strength is reflective of ASR-induced deterioration in the tensile strength of concrete. The figures show the ratio of the principal tensile concrete stress at cracking to the ACI 318 based concrete tensile strength for all panels with yellow. And it is also shown on this figure with green, the ratio of the measured ultimate shear strength for reactive panels to a comparable non-reactive panel. So it is clearly evident that while the concrete tensile strength was significantly reduced for the reactive panel with no out-of-plane reinforcement, the panel's ultimate shear strength was not adversely affected. And finally, for the range of conditions examined, the test results suggest the following conclusions. The shear stress at cracking is higher for reactive elements compared to non-reactive ones. For reactive elements containing biaxial reinforcement, the concrete principal tensile stress at cracking is significantly lower compared to that of non-reactive elements. Also, the ACI 218 predictions are unconservative. The shear strength of orthogonally reinforced elements is not negatively impacted by ASR-induced deterioration compared to similar non-reactive elements, regardless of the severity of expansion. A reduction in shear deformation capacity is common for ASR reactive elements compared to similar non-reactive ones. The orientation of shear cracks forms largely independent of the pre-existing ASR-induced cracks. The shear-induced cracks, however, propagate such that they breach the already existing ASR-induced cracks. The eventual mode of failure for reactive elements is not significantly different from that of similarly reinforced non-reactive elements. The reactive elements containing similar reinforcement ratio will exhibit similar responses, whether they show signs of ASR deterioration prior to the test or not. And finally, ASR is expected to compromise the long-term durability of concrete structures. So depending on exposure conditions, ASR-induced cracking can accelerate mechanisms such as chemical attack or reinforcement corrosion. Okay, this is the end of my presentation. Thank you very much for your attention.